In this video, we will learn how to find the firm's cost function given the production function and the price of inputs. The question is, consider a production function of a firm as Q is equal to twice under root K times L, where K and L are the units of capital and labor employed and Q is the output. If price of capital is $1 and price of labor is $4, we are supposed to find out the firm's cost function. Options are being given as q square, 2q, q or twice q square. We need to find out the correct option. Okay, so basically what we are being given, we are being given the production function, and let me write it here. Q is equal to twice k to the power 1 upon 2. We can write it in this fashion, L to the power 1 upon 2. Okay, price of capital is being given us as $1, price of labor is being given us as $4. We need to find out the total cost function, okay, for this firm. Now how do we solve this kind of question? Simple thing, we first set the cost minimization condition. That is, we minimize cost subject to the given production ISO count. That means our endeavor is to minimize cost, and we know cost is simply wage rate times units of labor employed plus rental rate of capital times units of capital employed. Okay, when we are being told price of labor is equal to 4, actually it is wage rate of the labor. And symmetrically, when we are being given price of capital is 1, that means it is our rental rate of capital is equal to 1. Okay, so the question is to minimize C is equal to WL. So in place of W we have 4L plus rental rate of capital is 1, so we write 1K, so it is K, subject to the production ISO count, that is twice K to the power 1 upon 2 L to the power 1 upon 2 should be equal to Q. Okay, then we can find out the cost function. Now we know the first order condition for minimization or optimization requires, and let's write it here. That is, or let's form the Lagrange's function here. Okay, we will solve it using the Lagrange's equation. That is, when we want to form the Lagrange's equation, first step is we rewrite the given production ISO count. Okay, so I can rewrite it in this fashion, that is Q minus twice K to the power 1 upon 2 L to the power 1 upon 2 should be equal to 0. After that, we multiply this resulting constraint by lambda. After that, we form out the Lagrange's function, and let's denote it by u here. Okay, so u is equal to, how do we form the Lagrange's function? Simply we add up the objective function. This is our objective function here, this cost function, and we add this resulting constraint to form the Lagrange's function. So our Lagrange's function will be 4L plus K plus we have this lambda. Okay, then this Q minus twice K to the power 1 upon 2 L to the power 1 upon 2, and this is our Lagrange function. Okay, now to find the optimal values of labor and capital, we partially differentiate this Lagrange's function with respect to labor, capital and lambda and set them equal to 0 simultaneously. That means first we find u subscript L, that means the partial derivative of this function with respect to labor. The derivative of L is 1, so we are left with 4 only. No L is involved here, so its derivative is 0. Here we have L in this equation in the third term. So what is the derivative of L to the power 1 upon 2? Let me write it here. So we have 1 upon 2 will become coefficient. Then we have let us write it in this fashion. It will become, we have first minus, okay, then we have lambda, then we have this 1 upon 2 will become coefficient 1 upon 2, then we have 2 k to the power 1 upon 2 L to the power minus 1 upon 2. Okay, this exponent is subtracted by 1 by power function rule. Here 2 and 2 will get cancelled, so we are left with u subscript L, which is the partial derivative of Lagrange's function with respect to labor, will be equal to 4 will be equal to, so this gets cancelled, we are left with lambda. 2 and 2 gets cancelled, we have k to the power 1 upon 2 L to the power minus 1 upon 2. Okay, and we set it equal to 0. This also set it equal to 0. Okay, or we can rewrite it in this fashion, that is lambda k to the power 1 upon 2 L to the power minus 1 upon 2 is equal to 4. Okay, after that, simple thing, again we take the partial derivative with respect to k of the with respect to, let me repeat it here. Good, cover. Next thing is to partially differentiate Lagrange's function with respect to L. So u subscript, with respect to k. Here no k is involved in the first term. Here derivative of k is 1, so we are left with 1. Again, derivative of k to the power 1 upon 2 will become, here we have lambda into minus is minus lambda. Exponent will become coefficient. First we have 2 k to the power minus 1 upon 2 L to the power 1 upon 2, and we set it equal to 0, or so we forgot to write it here. Okay, first exponent becomes coefficient, we have 1 upon 2 here, so we have 1 minus lambda and this 1 upon 2. Okay, again 2 and 2 gets cancelled, so we are left with 1 minus k to the power minus 1 upon 2 L to the power 1 upon 2, set it equal to 0, or k to the power minus 1 upon 2 L to the power 1 upon 2 is equal to 0. Okay, and obviously we have lambda here. Let us say this is equation 2. Now next thing would have been to partially differentiate with respect to lambda, so we don't require it here. So what will we do? Let us say this is equation first, second. Let us divide equation first by second, which implies, so equation first is lambda k to the power 1 upon 2 L to the power minus 1 upon 2 is equal to 4, divided by the second equation is lambda k to the power minus 1 upon 2 L to the power 1 upon 2 is equal to is equal to, here we have 4 divided by 1. Okay, so when we rewrite it, this when we transpose it here, it will become this stuff. Simple thing. Lambda gets cancelled. Transposing this k to the power minus 1 upon 2 to numerator, exponent sign will get changed and it will get multiplied because we have same basis here. So we have k to the power 1 upon 2 times k to the power 1 upon 2 in the numerator. Symmetrically transpose this to new denominator, so we have L to the power 1 upon 2, L to the power minus 1 upon 2 will become plus 1 upon 2, should be equal to 4. So bases are same, we can add up the exponents. It adds up to k upon L is equal to 4. Okay, which implies k is equal to 4L. After that we plug the value of k is equal to 4L into production constraint, so here, okay, which implies 2 k to the power 1 upon 2 means 4L to the power 1 upon 2. Then we have L to the power 1 upon 2 is equal to Q. So here we are left with 2 2s are 4, because 4 under root 2 is 2, so we have 2 into 2 is 4. L to the power 1 upon 2, L to the power 1 upon 2 is equal to Q. So we are left again, bases are same, we can add up the exponents. It becomes L is equal to Q, or L is equal to Q upon 4. Okay. After that, we plug the value of L is equal to Q upon 4 into the cost function. Okay, here. That means our C will be equal to, am I doing it correctly? Let me see. So L is equal to Q upon 4. No, what will we do? We again we have done this. Now let us do one thing here. So L is equal to this stuff. Now plug the value of L is equal to theta upon 4 first in this equation, okay, to get the value of K in terms of Q. So K will be equal to 4, L is Q upon 4, that is Q upon 4, 4 gets cancelled, so K is equal to Q, okay. Let me rub this out. This is not required yet. So we got K and L in terms of Q. Now we can find out the cost function. So our C is equal to, we know, plug the value of K and L into the cost function, that is into our objective function. This is our cost function, okay. So C will be equal to 4, the value of L is Q upon 4 plus K, again it is Q, 4 and 4 gets cancelled. That means C will be equal to, okay, so let us see, which implies C will be equal to Q plus Q, which implies C is equal to twice Q, okay. So the correct option should be, the cost function should be 2Q, okay. And let me repeat it here again. We were given the production function, and prices of the inputs, and we were required to find out the total cost function. First thing is what we did here. So this question was about cost minimization. We want to minimize cost, and we know cost is wage rate times units of labor plus rental rate of capital plus units of capital, okay, subject to the production constraint. So we have this production constraint. We set up the Lagrangian function, and Lagrangian function is set up. First, what will we do in this case? We set the production constraint equal to 0, multiplied by lambda, then add up this resulting constraint with the objective function. Our objective function is this cost function. So after adding these two, resulting constraint and objective function, we get this Lagrangian function. To find the optimal values of labor and capital, we partially differentiate Lagrangian function with respect to labor and capital and set them equal to 0, simultaneously solving them then, okay. So when we simultaneously solve them, we got K is equal to 4L. After that, we insert the value of K into the production constraint to get the value of L in terms of output, okay. After that, when we get L is equal to Q upon 4, we again plug the value of L in this equation to get K in terms of Q, and after that we can form the cost function, okay. So since C is equal to 4L plus K, L is the value of L is Q upon 4 plus the value of K is Q. Adding these two, we get C is equal to 2Q. I hope I make myself clear in this video. Thank you.